Hello everyone, I'm Jonathan Brand, an applications engineer here at Keysight working on ImSym. My background is in optical system design and integration. I'm excited to present today's webinar, Optimizing Imaging System Performance, Balancing Hardware and Software with ImSym. In today's talk, we're going to provide a quick introduction to ImSym's capabilities. We'll highlight how ImSym can what we call shift left your team's schedules and timelines, reducing your time to market, as well as budgeting and resourcing risks. We'll discuss challenges facing systems engineers and how they use the systems engineering V model to develop products. Then we'll jump into exploring a case study where distortion is a risk in a product's performance. We'll use ImSym to simulate the optical system, then measure, calibrate, and correct distortion of that optical system. We'll also show a live demo of the correction in action so you can see how easy it is to evaluate the virtual prototype's performance. Finally, we'll close out on other applications of ImSym as well as some concluding thoughts. For those who are new to ImSym, ImSym is Keysight's imaging system simulator released in 2024. ImSym is a software platform for modeling complete imaging system. It models the imaging chain in a quantitative way. Input scenes are represented as radiance fields in engineering units, watts per meter squared per steradian. The action of the lens on the input radiance field is represented from both an imaging performance and stray light performance perspective. Lens data for imaging is imported from Code 5 lens design software, and stray light data is imported from Light Tools, our non-sequential ray tracing tool. ImSym simulates the response of the sensor by taking the input irradiance, watts per meter squared, through calculations that represent the sensor's physical properties as well as the sensor noise. The action of the image signal processing algorithms is also controlled in ImSym and can either use preloaded algorithms or you can bring your own algorithms in via a Python interface. ImSym is a new product and therefore includes a new interface designed to be intuitive and user-friendly. It practically guides you through the modeling process. The results are presented conveniently to the user. This interface turns a very complex modeling process into an easy user experience. In current camera development landscapes, vendors rely heavily on real prototypes to assess the imaging quality of the camera they design, manufacture, and assemble. This traditional approach leads to long manufacturing cycles, suboptimal yields, and sometimes even costly redesign. With no efficient way to simulate the image quality of a camera, the development process is cumbersome and time-consuming. ImSym introduces a new simulation platform that enables a shift left for the camera system development through the realistic simulations. Shift left means that the majority of the product development is shifted from the manufacturing to software design. This gives the systems engineer and domain experts the ability to create virtual prototypes and see the effects from all components in the imaging system in a single simulation. This allows timelines to be completed faster and more cost-effectively by using simulations rather than traditional models that rely on physical prototyping and manufacturing. As I mentioned, my background is in optical system design. Many of the teams I've worked with in the past utilize the systems engineering V model to bring their solutions to market. This approach is applied to products of varying complexity, either products that are essentially a single optical system like a photographic camera, or something as complex as a robotic endoscope. Regardless of the complexity, both of these products face development risks. Traditionally, when we start off in our product design, we'll end up establishing what we would call user requirements, or what the product needs to do for the user. These requirements can either be qualitative or quantitative. Teams will use these user requirements to break down system requirements, subsystem requirements, leading eventually to component design. In the first portion of these component and subsystem designs, team will use software packages for their design work, including lens design software such as Code 5 and Light Tools, or other software such as EDA or CAD tools. Then, once they've completed the design revision they want to test in hardware, that's when they would begin multiple iterations of hardware design and testing. Teams would begin component verification and move up the right side of the V chart. This is where challenges can delay a team with build complexity, long lead times, or test method development. And so essentially, as teams move through the V model, they're using time and capital investment as they move from product definition decomposition through the integration for verification and validation, or commonly referred to as V&V. So, what are some of the risks that exist for optical systems? These are similar risks that exist for all product development projects. In some management philosophies, teams will face challenges of the triple constraint, where managing the three pillars of the project, the scope, the schedule, and the budget, are critical to the project's success. Examples of scope risks include requirement changes or competing product requirements. In some cases, this could be requirements that challenge packaging needs. Budget risks exist due to the availability of capital to spend on materials and labor. And finally, schedule risks include managing timelines impacted by internal and external milestones, long lead times for components, or delays in manufacturing prototypes. Where do virtual prototypes fit in the classic V model? As teams complete their component design, they can complete a design review against these simulated virtual prototypes. By replacing the initial hardware verification with simulations, we can greatly increase the success of a hardware integration cycle. Now, instead of teams traditionally moving from a component design into software and hardware development, teams can gate those hardware builds upon successful completion of a virtual V&V with the virtual prototype. The simulations reduce the need to re-execute prototype builds in the product development cycle. We also know that product development is cyclical, moving from proof of concept to engineering, transfer to manufacturing, and onto next generation design in some examples. Teams are applying the V model in each of these phases, however. Each phase can have a different user requirement, resulting in downstream impacts to the requirements and inevitably component designs. Some of these user requirements could affect durability, cost of goods, form factor changes, or the inclusion of new features, depending on the cycle that you're in. Small changes to the user needs related to the durability and cost of goods have a large impact on the optical design, impacting schedules and allocation of capital. By integrating simulations with ImSym, we believe you can shift left your schedule in any product development phase by de-risking the optical design in the applicable stage. So now let's look at a case study where distortion is a risk to the product. In this example, we assume that the lens designer completed the design shown below. This design meets all the technical requirements except a distortion specification, which in this case shows significant barrel distortion. However, upon evaluation, let's assume that redesigning the lens will result in a design that is not manufacturable on the current budget or schedule. So, instead of going back and revising the lens design, let's see if we can find an adequate software solution to address this deficiency. Before we simulate the camera, let's discuss our sensor. The detector selected for this webinar example is a 1/4 megapixel sensor meant to represent a commercially available sensor with reasonable noise characteristics. In this example, noise is not a critical factor, but in other applications, we appreciate the impact noise has on the final image. You can begin your simulations with our preloaded noise parameters and eventually replace that data with detailed design data, including color filter arrays, quantum efficiency, and spectral filters. You can also integrate the effects of relative angular response, but we will not cover those effects today. We have this initial design. Let's look at what is happening with the current images. On the left here, we have the original scene object and a corresponding zoom here in the middle. We've taken a picture of our friends, and when we look at the simulation through ImSym, we see something does not look right in the corner. Due to the distortion of the lens, the ImSym simulation shows our friend looks unnatural in the final image. For our application, this performance is not acceptable. As we mentioned before, we could update the optical design, but let's assume the solution is not manufacturable on our timeline or budget. Can we write an image signal processing block to accept a measurement of the distortion and calibrate the final image? This could allow the team to build hardware sooner and shift left their timeline with this situation. In order to do this, we'll need a distortion calibration. In a hardware environment, we would select a distortion target and take it to the bench and collect an image on the camera to measure the distortion. We can do the equivalent in ImSym. ImSym can accept any two-dimensional image in the form of a PNG or bitmap image. So in step 1, we designed a distortion grid pattern based on commercially available off-the-shelf targets. We can use it as a scene object input into ImSym. We can bring that simulation through ImSym with the simulated camera, and we can end up with the final image with a significant barrel distortion. This represents the uncorrected image that you would see if you were to build this camera in the real world with no correction, seen here in step 2. In step 3, we use the simulated output as the input into the calibration measurement. We wrote a Python routine to measure the difference between the simulated and paraxial image heights. By measuring the difference between these dots, we were able to plot the scene object location versus the image location in step 4. In this case, we fit a fifth-order polynomial to the curve as a representation for our distortion model. I want to make it clear that the software scripts that did this work were designed outside of ImSym. If you were to replicate this process, you could easily bring in your own team's expertise to this process. For example, you could bring in a more sophisticated distortion model to the analysis. Regardless of how simple or advanced the calibration model you use, this is what you could essentially employ on a manufacturing line. With this data, we proceed to step 5 and add a post-processing block to the image signal pipeline. ImSym allows you to use a custom ISP block via its Python interface and add in any image signal pipeline calculations you wish to add to your raw image. So in this case, we've designed a post-processing block to take the calibration parameter and apply it to the image in the image processing step. And so we can see here that the corrected image is a function of the original final image using the coefficients that we calculated in the previous slide. The ISP will take the original points and shift them outward based on these factors. ImSym is shipped with its own ISP that users can use. So here the ISP starts with the detector image, the pre-processing calibration, the white balance, demosaic, color conversion, and gamma correction. All of these were done with ImSym's internal ISP. And then we added the available post-process block, which we defined as the user to include the distortion calibration. This is where we add those calibrations, or you can add other calibrations as you please. However, you can customize everything between the output of the detector and the final image. As mentioned, we were going to add this ISP script. In the image signal processing pane of ImSym, we're able to add that distortion correction Python routine to the ISP itself. And what we see here is we have our original scene object on the left, and then we have the original final image output with no correction. But on the right here, we have the correction to the ISP with the distortion correction in play. Here we see that the distortion has been greatly reduced by that correction. Let's look at the impact of the custom ISP on the original scene object. The original scene object that we had was this image of our friends, and with them looking like this in the corner. When we had our original ISP with no correction, we had this deformity in the corner that clearly showed in the final image. On the right, we have our final image with our distortion correction, where we no longer have this distortion effect affecting the final image. So, what now? We can now inform our hardware and software choices with ImSym. With a completed ISP solution, we have two viable solutions to address our distortion issue. We can either elect to build the lens as is and implement the software solution that we just saw, or we can elect to redesign the lens if we determine the challenge of implementing a software change if the challenges are too complicated. The value ImSym adds is the ability to fully simulate and visualize hardware, software, and firmware solutions on a single software platform. You and your team now have quantifiable data you can make decisions with. So now I'd like to go into a live demonstration of ImSym and show what those changes were looking like. So we have ImSym open here, and I loaded in our distortion grid into the program as the scene object. When we load in a lens from code 5, we get this 3D image representation of the lens itself. Here we have the detector layout where we have the pixels in X and Y, their size, as well as our filters defined here. And you can see we have our regular noise setting selected. Initially, we're using ImSym's default ISP, and we have the simulation loaded here complete, where we have the principal image, the output of the detector in RAW, and then this is the final image through the ISP. What I've already done is taken this final image and done the calculation for the calibration and imported that calibration into a fifth order correction for the distortion in the custom ISP. So to apply this correction to the ISP, all I have to do is load in this Python script and select custom ISP and come back to our simulation. And now I've run the simulation through the ISP with that distortion correction, and we can see that the distortion in this final image is much improved over what we just saw. And so now we're going to move on to the second part of this demonstration where we show the result with the scene object we saw of our two friends. So here I've loaded the project now with our original scene object of our two friends. All the other settings are the same, such as the field of view and the spectrum definition. The lens model is the same. The detector settings are the same and the same noise parameters. And I'm going to start with the original default ISP. Here's our simulation with our principal image. We can see the distortion effect in the principal image. And we see that output of the detector image also has the distortion impact. Our final image has this as well. So now if we go back into the image signal processing pane and switch to our custom ISP that has the same settings as we showed previously, and come back and rerun the simulation, we now can see that the distortion in the corner here is much better. And so this is the impact of using that custom ISP and calibration on the final image. And I can quickly move between the scene object and the simulation. Now we get some clipping because the field of view with the sensor is smaller than that of the original scene object, but that's to be expected. How else can ImSym help us when parts are being built in the real world? We've already simulated image quality assessment. A team can also accelerate the development of their test methods using ImSym. Our manufacturing systems follow the V model for development as well. Using ImSym, we can simulate the images that are used by the end-of-line test station, or engineers can import image quality test targets as scenes into ImSym. By combining tolerance analysis from Code 5 and ImSym sensor models, you can test the variation in your test methods. Therefore, as manufacturing stations have the ability to come online faster, because instead of waiting for first hardware samples to arrive to testing facilities, you can simulate the manufacturing test using ImSym. We view ImSym as an expansion of your tools if you already use Code 5 or Light Tools. Code 5, for example, is a powerful lens design tool capable of outputting nominal or tolerance lens designs that mimic real-life variation. Light Tools allows you to incorporate stray light sources and unique lighting conditions to your model. ImSym, however, takes these inputs from these systems, allowing systems engineers to assess the final impact of the design choices at the system level, mimicking real-life performance. ImSym should play a critical role in any optical imaging design project because it provides a complete system simulation from the object to the final image, including all impacts of hardware and image signal processing. ImSym's speed is greatly impacted by the use of GPUs. The work presented in this talk was performed on a laptop with an Intel Core Ultra 7 with 32 gigabits of RAM and the NVIDIA RTX 2000 GPU. A 1/4 megapixel sensor took less than 1 minute to complete the simulation from principal image to the final image. Subsequent simulations where the principal image was unchanged took less than 5 seconds, as we saw in our demos. However, GPUs offer potential improvements of up to 100 times depending on the GPU selected. In this graph on the right, we look at 5 different GPUs of varying compute power. Each GPU has a different number of teraflops, where more teraflops means more compute power. As we're able to see across different object resolutions from 5 megapixel up to 140 megapixels, potential improvements of up to 100 times faster are possible with the selection of the correct GPU. In conclusion, ImSym can simulate a wide variety of image quality calibrations and tests. In our example, we were able to correct the distortion error in the ISP without updating the lens design. However, your team can employ this approach how you see fit. Your team will determine the best path forward as to what tests to employ. This requires an understanding of your complete system, your user requirements, your component design, and your verification and calibration methods you have available. By including ImSym to balance solutions using hardware and software, you can accelerate your product design and manufacturing activities based on your users' requirements. So, where can you learn more? If you are a new user and want to arrange a trial of ImSym, you can send an email to optics@keysight.com. If you are already a user of our products, you can find more learning material through learnopticalsolutions.keysight.com. There you can find resources and training on all of our software. And if you want to arrange a trial of a specific product, you can send an email to optics@keysight.com. This concludes our webinar, and thank you for attending.